Welcome to Sleepy Science Odyssey. Tonight, universe mysteries. The profound unknowns of cosmology and astrophysics. From the nature of dark matter that outweighs visible matter 5 to 1 to the dark energy accelerating cosmic expansion. From the information paradox of black holes to the fine-tuning of physical constants. From the origin of the universe in the Big Bang to the possibility of multiverses, from the silence in our search for extraterrestrial intelligence to the measurement disagreements in the Hubble constant. From the matter-antimatter asymmetry to the arrow of time, we'll explore what we know, what puzzles remain, and why these mysteries matter for understanding existence itself. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real cosmology and physics, no exaggeration, just quiet facts in the dark. Let's begin. Dark matter comprises approximately 85% of the universe's matter, but has never been directly detected despite decades of searching. The existence of dark matter is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Yet its fundamental nature remains one of cosmology's deepest mysteries. Understanding what dark matter is, what particles compose it, how they interact, where they came from, would revolutionize physics and astronomy while illuminating the structure and evolution of everything from galaxies to the cosmos itself. The first evidence for dark matter came from observations of galaxy rotation curves in the 1970s by Vera Rubin and others. According to Newton's laws, stars orbiting far from a galaxy's center should move more slowly than those closer in, just as outer planets orbit the sun more slowly than inner planets. However, observations revealed that rotation speeds remain roughly constant or even increase with distance from galactic centers. This implied the presence of substantial unseen mass extending well beyond the visible galaxy, creating gravitational fields that accelerate outer stars. Galaxy cluster dynamics provide additional evidence for dark matter. Fritz Zwicky in the 1930s observed that galaxies in the Coma cluster moved too fast to be bound by the gravity of visible matter alone. They should have escaped the cluster long ago. The velocities implied total cluster, mass approximately 100 times greater than visible mass. Modern observations of many clusters confirm this pattern. Visible matter comprises only approximately 15 to 20% of total gravitational mass. Gravitational lensing, the bending of light by massive objects predicted by general relativity, offers independent dark matter evidence. Background galaxies appear distorted around foreground clusters, with the distortion magnitude depending on the total mass, not just visible mass. Mapping these distortions creates mass maps showing that clusters contain far more mass than visible matter can account for. The Bullet cluster provides particularly striking evidence. Two galaxy clusters that collided and passed through each other show separated distributions of visible matter and gravitational mass, with dark matter apparently passing through while normal matter interacted and slowed. Cosmic microwave background, or CMB observations, reveal dark matter's role in structure formation. The CMB is thermal radiation from approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. Tiny temperature fluctuations in the CMB, variations of approximately 1 part in 100,000, represent density fluctuations that later grew into galaxies and clusters. The pattern of these fluctuations depends on the universe's composition, and detailed measurements by satellites including WMAP and Planck precisely determine dark matter abundance at approximately 27% of total cosmic energy density. Big Bang nucleosynthesis, the formation of light elements in the early universe, constrains the amount of ordinary matter or baryonic matter. The abundances of hydrogen, helium, deuterium, and lithium produced in the first few minutes after the Big Bang depend sensitively on baryon density. Observations of these primordial abundances indicate baryonic matter comprises only approximately 5% of cosmic energy density. Combined with other measurements showing total matter is approximately 32%. This implies approximately 85% of matter is non-baryonic dark matter. The nature of dark matter particles remains unknown despite numerous candidates. Weakly interacting massive particles, or WIMPs, represent perhaps the most studied candidate class. WIMPs would have masses from approximately 10 to 1,000 times the proton mass and interact via the weak nuclear force and gravity. This interaction strength naturally produces the observed dark matter abundance through thermal freeze-out in the early universe, a WIMP miracle, making them theoretically attractive. However, direct detection experiments searching for WIMP interactions with ordinary matter have found no convincing signals despite increasing sensitivity. Direct detection experiments typically use large masses of extremely pure materials in deep underground laboratories to shield against cosmic rays. When a dark matter particle collides with a nucleus in the detector, it deposits energy that can be measured as heat, ionization, or light. Experiments including LUX, xenon, and super-CDMS have pushed sensitivity to extraordinary levels, testing large portions of WIMP parameter space, yet no definitive dark matter signal has emerged. Each null result constrains WIMP properties, narrowing the allowed parameter space. Axions represent an alternative dark matter candidate with very different properties than WIMPs. Axions are extremely light particles, potentially billions of times lighter than electrons, originally proposed to solve the strong CP problem in particle physics. If they exist with appropriate properties, they could be produced in the early universe in sufficient abundance to constitute dark matter. Axion detection experiments use fundamentally different techniques than WIMP searches, typically looking for axion conversion to photons in strong magnetic fields. Experiments including ADMX are actively searching for axions across different mass ranges. Sterile neutrinos, hypothetical particles that interact only through gravity and possibly the weak force, represent another candidate. Unlike the three known neutrino types that interact through the weak force, sterile neutrinos would be nearly invisible, interacting primarily through gravity. With appropriate masses, perhaps 1 to 10 kiloelectron volts, sterile neutrinos could constitute dark matter. Some astronomical observations hint at possible sterile neutrino signatures, including an unexplained X-ray emission line at approximately 3.5 kiloelectron volts from galaxy clusters, though interpretations are controversial. Primordial black holes formed in the very early universe rather than from stellar collapse, have been proposed as dark matter candidates. If density fluctuations in the early universe were large enough in certain regions, those regions could collapse directly into black holes. Depending on formation conditions, primordial black holes could have masses ranging from subatomic to thousands of solar masses. Gravitational lensing observations constrain primordial black hole abundances in many mass ranges, excluding them as the dominant dark matter component for most masses, though some windows remain open. Modified gravity theories propose that dark matter doesn't exist, and instead, our understanding of gravity is incomplete. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram, modifies Newton's laws at very low accelerations to reproduce galaxy rotation curves without dark matter. MOND successfully fits many galaxy observations with a single parameter, but struggles with galaxy clusters and cosmological observations. Relativistic extensions of MOND, including TVS, attempt to incorporate general relativity while preserving MOND's successes, but none have matched dark matter's broad explanatory power. The small-scale structure problem refers to discrepancies between dark matter simulations and observations. Lambda CDM, the standard cosmological model with cold dark matter and dark energy, predicts more small satellite galaxies around large galaxies than are observed, predicts dark matter halos should have cuspy central density profiles, while many observed galaxies have flatter cores, and predicts the most massive satellites should be denser than observed. These discrepancies might indicate problems with dark matter models, or they might reflect complex baryonic physics poorly captured in simulations, or they might require dark matter with different properties than assumed. Self-interacting dark matter, or SIDM, proposes that dark matter particles interact with each other through forces beyond gravity, potentially solving small-scale structure problems. If dark matter has weak self-interactions, particles would collide and scatter within galaxy halos, heating the central regions and creating flatter density cores. The interaction strength would need to be small enough not to disrupt larger-scale structure, but large enough to affect galactic cores. Simulations show SIDM can alleviate several small-scale problems, making it an active research direction. Fuzzy dark matter proposes that dark matter consists of extremely light bosons, perhaps 10 to the negative 22 electron volts, that behave quantum mechanically on galactic scales. The uncertainty principle would prevent these particles from being localized to small regions, creating de Broglie wavelengths of kiloparsec scales. This would smooth out small-scale structure, potentially addressing problems that plague standard cold dark matter. Fuzzy dark matter makes distinctive predictions for halo structure that can potentially be tested with observations. The dark matter distribution in the Milky Way affects direct detection prospects. The Sun orbits the galactic center at approximately 220 kilometers per second, plowing through the dark matter halo. Direct detection rates depend on the local dark matter density and velocity distribution, both uncertain. If dark matter forms streams or has complex substructure, detection rates could vary with time or direction in ways that might be observable. Understanding local dark matter distribution requires combining observations of stellar motions, galactic structure modeling, and simulation results. Dark matter's role in galaxy formation and evolution is profound. In the current paradigm, dark matter halos form first through gravitational collapse of small perturbations in the early universe. These halos then merge hierarchically, creating larger structures. Baryonic matter falls into dark matter potential wells, cools, and eventually forms stars and galaxies. Without dark matter providing gravitational scaffolding, galaxies as we know them could not form. The properties of galaxies, sizes, rotation speeds, star formation histories, all reflect their dark matter halos. The distribution of dark matter across cosmic scales creates the cosmic web, the large-scale structure of the universe. Dark matter filaments connect clusters, with galaxies forming along these filaments and at their intersections. Vast voids with little dark matter separate the filaments. This web-like structure is visible in galaxy surveys and matches predictions from dark matter simulations. The overall pattern provides strong evidence that dark matter exists and drives structure formation, even if we don't know what it is. The possibility of dark matter being composed of multiple particle types has gained attention. Just as ordinary matter includes protons, neutrons, electrons, and photons with different properties, dark matter might comprise multiple particle species. Some could be heavy WIMPs, others light axions, creating a dark sector mirroring ordinary matter's complexity. This would explain why no single candidate has been detected. We're searching for one component while others contribute to the total. However, this adds complexity, requiring multiple detection strategies. Dark photons, hypothetical force carriers mediating interactions between dark matter particles, represent another theoretical possibility. If dark matter particles carry dark charge, analogous to electric charge, dark photons would mediate their interactions, creating a dark electromagnetic force. These dark photons might occasionally mix with ordinary photons, providing a detection mechanism. Experiments search for dark photons through missing energy signatures in particle collisions or resonances in photon scattering experiments. The annual modulation signal, reported by the DAMA Libra experiment, presents a persistent puzzle. This experiment observes an annual variation in detection rate that could result from Earth's motion through the dark matter halo. When Earth's orbital motion aligns with solar motion through the halo, detection rates should increase. DAMA has observed this modulation for over 2 decades. However, other experiments testing similar parameter space find no signals, creating tension. Whether DAMA has detected dark matter through an unexpected channel, or whether the signal has other origins remains unresolved. Dark energy drives the accelerating expansion of the universe, but its nature is completely unknown. The discovery that the universe's expansion is accelerating rather than decelerating represents one of the most surprising and mysterious findings in science. This acceleration implies the existence of dark energy, a component with negative pressure that constitutes approximately 68% of the universe's total energy density. Understanding dark energy is essential for predicting the universe's ultimate fate and may require revolutionary changes in physics. The evidence for accelerating expansion came from observations of type Ia supernovae, exploding white dwarf stars that serve as standard candles with known intrinsic brightness. By measuring their apparent brightness, astronomers can determine distances. 2 independent teams in 1998 measured distances to distant supernovae and found they were fainter than expected, implying greater distances than cosmological models with only matter predicted. The supernovae were farther away because the universe's expansion had accelerated, stretching space more than expected. Type Ia supernovae occur when white dwarfs, dense remnants of stars like the Sun, accrete matter from companions and exceed the Chandrasekhar limit of approximately 1.4 solar masses, triggering runaway nuclear fusion that destroys the star. Because this occurs at a consistent mass, the explosions have similar peak luminosities, making them useful distance indicators after accounting for a relationship between luminosity and decline rate. Measuring supernovae across cosmic time reveals how expansion rate has changed. The data show expansion was decelerating in the early universe, but began accelerating approximately 5 to 6 billion years ago. The cosmological constant lambda represents the simplest dark energy model. Einstein introduced the cosmological constant in 1917 as a modification to general relativity, allowing static universe solutions. He later called it his greatest blunder after the universe's expansion was discovered. A cosmological constant represents vacuum energy, energy inherent to empty space that remains constant as the universe expands. Unlike matter whose density decreases as the universe grows, vacuum energy density stays constant, so it becomes increasingly dominant as matter dilutes. This causes accelerating expansion. The value of the cosmological constant required to explain observations is extraordinarily small, approximately 10 to the negative 47 inverse square meters, or equivalently, approximately 6 times 10 to the negative 10 joules per cubic meter. This corresponds to an energy density of approximately 70% of the universe's critical density. This value poses a profound theoretical puzzle because quantum field theory calculations of vacuum energy yield values approximately 10 to the 120 times larger, perhaps the worst prediction in physics. Understanding why the cosmological constant is so small represents a major unsolved problem. The cosmological constant problem asks why vacuum energy is so much smaller than predicted. Quantum field theory suggests that even empty space contains quantum fluctuations, virtual particles popping in and out of existence, contributing to vacuum energy. Summing contributions from all fields and all energy scales up to the Planck scale yields enormous vacuum energy. Yet the observed cosmological constant is tiny. Proposed solutions include unknown cancellation mechanisms, anthropic arguments that only universes with small cosmological constants allow galaxy and star formation, or modifications to quantum field theory at high energies. The coincidence problem asks why dark energy and matter densities are similar today. For most of cosmic history, either radiation or matter dominated the universe's energy density. Dark energy was negligible. But in recent cosmic time, dark energy became comparable to matter and then dominant. That we live in the brief cosmic epoch when densities are similar seems suspicious. This coincidence might indicate that dark energy is not a cosmological constant, but instead varies with time in ways that create temporary comparability. Dynamical dark energy models attempt to address this. Quintessence models propose that dark energy is a dynamical field rather than a cosmological constant. In these models, a scalar field with potential energy varying slowly over time acts as dark energy. Different potential shapes lead to different expansion histories. Quintessence can address the coincidence problem if the field is constructed such that its energy density tracks matter density for some period before becoming dominant. However, quintessence models require fine-tuning of initial conditions and potential shapes, merely trading one fine-tuning problem for another. Phantom energy represents hypothetical dark energy with equation of state parameter W less than -1, where W relates pressure to energy density. A cosmological constant has W equal to exactly -1, while quintessence typically has W greater than -1. Phantom energy would lead to increasingly rapid expansion, potentially ending in a big rip where expansion becomes so violent that galaxies, stars, atoms, and eventually spacetime itself are torn apart. Current observational constraints on W are consistent with -1, but allow some range for phantom, or quintessence-like behavior. Modified gravity theories propose that dark energy doesn't exist, and instead general relativity fails on cosmic scales. These theories modify Einstein's equations to produce accelerating expansion without requiring dark energy. Examples include F-R gravity, where the Einstein-Hilbert action is modified, scalar tensor theories, where gravity is mediated by both the metric and scalar fields, and massive gravity, where the graviton has non-zero mass. These theories must reproduce general relativity's successes in the solar system while producing acceleration on cosmological scales, a challenging requirement. The degravitation idea suggests that gravity becomes weaker on very large scales, reducing the attraction that would normally decelerate expansion. Implementing degravitation in a theoretically consistent way that matches observations has proven difficult. Extra-dimension models, including brain-world scenarios, propose our universe is a four-dimensional brain embedded in higher dimensional space, with gravity leaking into extra dimensions on large scales, potentially explaining accelerated expansion without dark energy. These models make predictions that can potentially be tested. Measurements of cosmic expansion history through multiple independent methods test dark energy models. Besides type Ia supernovae, baryon acoustic oscillations or bows in the distribution of galaxies provide a standard ruler, a characteristic scale imprinted by sound waves in the early universe. Measuring the apparent size of this scale at different cosmic times reveals expansion history. Weak gravitational lensing, the subtle distortions of distant galaxy images by foreground matter, probes both expansion history and structure growth. Combining these methods constrains dark energy properties. The Hubble constant tension represents a puzzle potentially related to dark energy. The Hubble constant H0 describes the current expansion rate. Measurements from the cosmic microwave background using Planck's satellite data yield approximately 67 kilometers per second per megaparsec. Measurements from local type Ia supernovae using Hubble Space Telescope data yield approximately 73 kilometers per second per megaparsec. This approximately 9% discrepancy exceeds measurement uncertainties and persists despite careful checks. If not due to systematic errors, the tension might indicate new physics, including evolving dark energy or additional relativistic particles in the early universe. Large-scale structure observations constrain dark energy through its effect on structure growth. Dark energy's negative pressure opposes gravitational collapse, slowing the growth of cosmic structure. Comparing predictions for structure growth from the CMB with observations of structure at later times tests dark energy models. Galaxy surveys including SDSS and upcoming surveys like LSST and Euclid will provide precision measurements of structure growth and expansion history, potentially distinguishing between cosmological constant and dynamical dark energy. The ultimate fate of the universe depends on dark energy's nature. If dark energy is a cosmological constant, expansion will continue accelerating forever. Galaxies outside our local group will recede beyond our cosmic horizon, becoming forever unobservable. Star formation will eventually cease as gas is depleted. Stars will burn out, leaving black holes, neutron stars, and black dwarfs. Eventually, even black holes will evaporate through Hawking radiation on timescales of 10 to the 100 years or more. The universe will approach a cold, dark, dilute state, heat death. If dark energy is phantom energy with W less than -1, expansion could accelerate so rapidly that it overcomes all forces, tearing apart structures in a big rip. galaxies would be disrupted first as expansion overcomes gravity binding them. Eventually, stars, planets, and atoms would be torn apart as expansion overcomes electromagnetic and nuclear forces. Finally, space-time itself might be disrupted. However, current constraints on W make such extreme scenarios unlikely, though not excluded. If dark energy is dynamical and could decay or reverse sign, more complex fates are possible. Dark energy might decay into matter or radiation, reheating the universe. It might reverse sign, causing expansion to decelerate and potentially leading to recollapse in a big crunch. Such scenarios require specific quintessence models and face theoretical challenges, but illustrate that the universe's fate is not settled. Understanding dark energy determines whether the universe has a finite or infinite future, and whether current conditions are typical or transient. The interaction between dark energy and dark matter, if it exists, could provide clues to both components' nature. Coupled dark energy models propose that dark energy and dark matter exchange energy, with coupling strength determining whether matter density affects dark energy evolution or vice versa. Such coupling could address the coincidence problem by creating temporary tracking behavior. However, coupling is tightly constrained by observations of structure formation and must be weak if present. Early dark energy models propose that dark energy was not entirely negligible in the early universe, contributing a few percent of total energy density. This could potentially address the Hubble tension if early dark energy altered expansion history in ways that reconcile early and late time measurements. However, early dark energy faces constraints from CMB observations and must avoid disrupting the successful predictions of standard cosmology for structure formation and nucleosynthesis. The relationship between dark energy and the vacuum catastrophe extends to questions about quantum gravity. If quantum gravity modifies quantum field theory at high energies in ways that alter vacuum energy calculations, the catastrophically large predictions might be avoided. String theory landscapes propose approximately 10 to the 500 different vacuum states with different cosmological constants, though which vacuum the universe occupies and why remain mysterious. These approaches attempt to make dark energy less mysterious by embedding it in broader theoretical frameworks, though success is debated. Black hole information paradox questions whether information is destroyed when matter falls into black holes, potentially violating quantum mechanics. Black holes represent regions where gravity is so strong that nothing, not even light, can escape. According to general relativity, anything crossing a black hole's event horizon, the boundary of no return, is inevitably pulled to the singularity at the center, where known physics breaks down. This leads to profound questions about information, entropy, and the consistency of physical laws, with the information paradox representing perhaps the deepest puzzle about black holes. The Noether theorem states that black holes are characterized by only three quantities: mass, electric charge, and angular momentum, their hair. All other information about matter that formed the black hole or fell into it is lost, according to classical general relativity. A black hole formed from a star looks identical to one formed from collapsed gas or antimatter, provided the three quantities match. This seems to imply that enormous amounts of information about the matter that formed or entered the black hole has disappeared. Hawking radiation complicates the picture. In 1974, Stephen Hawking calculated that quantum effects near event horizons cause black holes to emit thermal radiation. Virtual particle pairs, quantum fluctuations that normally annihilate immediately, can be separated by the black hole's gravity, with one particle falling in and the other escaping as Hawking radiation. This radiation carries energy away, causing the black hole to slowly evaporate. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Stellar mass black holes are extraordinarily cold, but microscopic black holes would be hot. The information paradox arises because Hawking radiation is thermal, completely random, and carrying no information about what fell into the black hole. If a black hole evaporates completely via Hawking radiation, emitting purely thermal radiation until nothing remains, information about everything that fell in appears destroyed. This violates quantum mechanics, which holds that information is conserved. Pure quantum states evolve into pure states, and knowing the final state should allow reconstructing the initial state. Destroying information would violate this unitarity principle fundamental to quantum theory. The paradox forces a choice between seemingly fundamental principles. Either information is destroyed, violating quantum mechanics, or information somehow escapes in Hawking radiation, which appears impossible since radiation from outside the horizon shouldn't know what's inside, or the evaporation doesn't complete and a remnant preserving information remains, or something else happens we don't understand. Each option has problems, making the paradox particularly vexing. Black hole complementarity, proposed by Leonard Susskind and others, suggests information is both reflected at the horizon and crosses it, two complementary descriptions that cannot be simultaneously observed. An outside observer sees information encoded in horizon degrees of freedom, eventually re-emitted in Hawking radiation. An infalling observer sees nothing special at the horizon and sees information cross and hit the singularity. These descriptions seem contradictory, but like complementarity in quantum mechanics, both might be valid from different perspectives. This proposal is controversial and not universally accepted. The firewall paradox emerged in 2012 when researchers argued that black hole complementarity leads to contradictions. For information to escape in Hawking radiation, Hawking particles must be entangled with particles inside the black hole. But quantum mechanics forbids a particle from being maximally entangled with two partners simultaneously, the monogamy of entanglement. Resolving this seems to require a firewall, a wall of high-energy particles at the event horizon. That would violate the equivalence principle, which states that freely falling observers experience no local gravitational effects. The firewall paradox remains unresolved. The holographic principle proposes that all information in a volume of space can be encoded on its boundary. This idea emerged from black hole thermodynamics, which found that black hole entropy, a measure of information, is proportional to horizon area, not volume. If this holds generally, a three-dimensional region contains no more information than a two-dimensional boundary. The AD-SCFT correspondence, a realization of holography, relates gravitational theories in anti-de Sitter space to non-gravitational quantum field theories on the boundary, providing concrete examples where holography is precisely defined. The page curve describes how black hole entropy should evolve during evaporation if information is conserved. Initially, as the black hole evaporates and emits radiation, entropy increases as more radiation is produced. However, at the page time, halfway through evaporation, entropy should begin decreasing as information starts being retrieved from the radiation. Eventually, when evaporation completes, Entropy should return to zero if information is fully recovered. Recent calculations using quantum gravity approaches suggest the page curve can be reproduced, supporting information conservation, though details are debated. Soft hair proposals suggest black holes have more structure than the no-hair theorem indicates. Soft, very low energy, photons and gravitons can add infinite amounts of information to black holes without changing mass, charge, or spin measurably. This soft hair might carry information about what fell in, potentially allowing information to escape via Hawking radiation while preserving the equivalence principle. However, whether soft hair provides sufficient information storage and retrieval mechanisms remains unclear. Wormholes have been invoked in some information conservation proposals. The equals Epper conjecture suggests that entangled particles are connected by tiny wormholes, Einstein-Rosen bridges. For black holes, entanglement between Hawking particles and interior modes might correspond to wormholes connecting them, potentially providing pathways for information to escape. These wormholes would be non-traversable, nothing could travel through them, but might allow information transfer through quantum effects. The proposal is speculative and requires quantum gravity for full description. Loop quantum gravity approaches to black holes suggest the singularity is replaced by a high-curvature region where quantum geometry effects dominate. Depending on formulation details, infalling matter might bounce or tunnel through to another region, potentially avoiding information destruction. However, whether information can escape to the exterior universe during evaporation remains unclear in these models. Loop quantum gravity black holes might leave Planck-scale remnants containing information, though remnants face theoretical challenges. String theory provides frameworks addressing the information paradox. Early work by Strominger and Vafa counted microscopic states of certain black holes, matching Bekenstein-Hawking entropy and suggesting that information is encoded in these states. Recent work using AD-SCFT correspondence suggests information is preserved and can be computed using boundary theory descriptions. However, realistic black holes differ from the special cases where detailed calculations are possible, leaving questions about general applicability. Experimental tests of information conservation in black holes are extraordinarily difficult. Hawking radiation from stellar mass black holes is far too weak to detect. Black holes are typically much warmer than their surroundings, absorbing more radiation than they emit. Detecting information-carrying correlations in Hawking radiation requires measuring quantum properties across vast separations and long times. Analog black holes, systems like flowing fluids or Bose-Einstein condensates that mimic black hole horizons, might provide testable analogs, with some experiments reporting analog Hawking radiation, though connections to real black holes are debated. The information paradox connects to broader questions about quantum gravity. Black holes provide arenas where quantum mechanics and general relativity meet inescapably. Quantum effects produce Hawking radiation, while gravitational effects create horizons and curvature. Resolving the paradox likely requires understanding quantum gravity, the theory unifying quantum mechanics and general relativity. Different quantum gravity approaches, string theory, loop quantum gravity, causal set theory, and others, offer different perspectives on the paradox. The role of observer perspective in the information paradox highlights deep questions about quantum measurement and reality. If information appears lost from an external observer's perspective, but preserved from other perspectives, what constitutes physical reality? Does objective reality exist independent of observers, or is reality observer-dependent? These philosophical questions connect to interpretations of quantum mechanics and may require new frameworks for thinking about physics in quantum gravitational contexts. Black hole entropy and thermodynamics provide crucial clues about quantum gravity and the information paradox. The Bekenstein-Hawking entropy formula S equals Ka/4L p squared, whereas horizon area and Lp is Planck length, suggests that black hole information content scales with area, not volume. This area scaling motivated the holographic principle. Understanding the microscopic origin of black hole entropy, what degrees of freedom create this entropy, remains a key goal, with different quantum gravity approaches offering different microscopic descriptions. The fine-tuning of physical constants for life raises profound questions about why the universe is suitable for complexity and observers. The fundamental constants of physics, quantities like the strength of gravity, the mass of the electron, the cosmological constant, and many others, appear fine-tuned in the sense that small changes would produce universes dramatically different from ours, often incompatible with any form of complexity or life. This fine-tuning is not proof of design, but presents a genuine scientific puzzle about why our universe has the properties it does. The strength of gravity relative to other forces demonstrates fine-tuning. Gravity is extraordinarily weak, approximately 10 to the 39th times weaker than electromagnetism. This weakness allows large structures to form before collapsing to black holes and allows long-lived stars. If gravity were much stronger, stars would burn out quickly, potentially before complex chemistry could develop. If much weaker, matter might not clump into stars and planets. The specific value seems necessary for a universe with long-lived stars supporting planetary systems where life could evolve. The cosmological constant fine-tuning is perhaps most striking. As mentioned earlier, quantum field theory predicts vacuum energy approximately 10 to the 120 times larger than observed. If the cosmological constant were only modestly larger than observed, say 10 times larger, it would have dominated expansion when the universe was much younger, preventing galaxy formation. If it were negative and had similar magnitude, the universe would have recollapsed before stars formed. The observed value seems extraordinarily special, allowing billions of years of structure formation. The ratio of electromagnetic to gravitational force affects stellar structure and evolution. This ratio determines the balance between gravitational contraction and thermal pressure in stars. If the electromagnetic force were slightly stronger or weaker relative to gravity, stellar lifetimes could be drastically shorter, or nuclear fusion might not occur efficiently, or stable stars might not form. The specific ratio allows stars to burn steadily for billions of years, providing stable energy sources for planets. The strength of the strong nuclear force determines nuclear stability. If the strong force were approximately 2% stronger, protons could bind into diprotons, two-proton nuclei without neutrons. This would alter stellar nucleosynthesis dramatically and might prevent hydrogen from persisting, eliminating water and organic chemistry as we know them. If the strong force were a few percent weaker, deuterium, heavy hydrogen, might not be stable, affecting nucleosynthesis pathways and potentially preventing formation of elements necessary for life. The neutron-proton mass difference of approximately 0.1% appears fine-tuned. This difference, slightly larger than the electron mass, allows free neutrons to decay while neutrons bound in most nuclei are stable. If the difference were smaller, hydrogen might decay into neutrons, eliminating the most abundant element. If larger, more complex nuclei might be unstable. The specific value allows both hydrogen and heavy element stability necessary for chemistry. Carbon and oxygen abundance, fine-tuning, involves nuclear resonances. Carbon forms in stars through the triple alpha process, where 3 helium nuclei combine. This process is enhanced by a resonance in carbon-12 at approximately 7.65 MeV, an energy level allowing the reaction to proceed efficiently. Fred Hoyle predicted this resonance based on the necessity of producing carbon for life before it was experimentally confirmed. Oxygen production involves additional nuclear reactions, and if certain energy levels were slightly different, either carbon or oxygen might dominate, potentially precluding both, which are necessary for organic chemistry. The dimensionality of space, 3 spatial dimensions, might itself be fine-tuned. In 2 spatial dimensions, complex structures seem impossible. For example, digestive tracts would disconnect organisms. In 4 or more spatial dimensions, planetary orbits are unstable. Planets would spiral into or away from stars rather than maintaining stable orbits. Atoms might be unstable in higher dimensions, as electron orbits could be non-stable. 3 dimensions allow both stable orbits and complex structures necessary for life. The number of space-time dimensions also affects field theories. In 3 spatial dimensions, inverse square laws govern forces. Gravitational and electric field strengths fall off as 1 over distance squared. This specific fall-off allows stable structures. In higher dimensions, different power laws apply, potentially preventing stable atoms or orbits. Some theories, including string theory, propose additional spatial dimensions, but they must be compactified, curled up to microscopic scales, to allow our 3-dimensional experience. The hierarchy problem in particle physics represents fine-tuning of a different sort. The Higgs boson mass is approximately 125 GeV, far below the Planck scale of approximately 10 to the 19 GeV, where quantum gravity effects become important. Quantum corrections to the Higgs mass should drive it toward the Planck scale unless there's extraordinary cancellation among contributions, fine-tuning to many decimal places. Proposed solutions include supersymmetry, which provides cancellation mechanisms, or compositeness, where the Higgs is not elementary, or anthropic selection among a landscape of possibilities. The flatness problem represents cosmological fine-tuning. The spatial curvature of the universe is extremely close to 0. The universe is flat or nearly flat. This requires the energy density very early in cosmic history to match the critical density with extraordinary precision. Deviations larger than approximately 1 part in 10 to the 60 at Planck time would have grown, creating strongly curved universes unlike ours. Inflation solves this by stretching any initial curvature to negligible levels. But then the question becomes why inflation occurred and why it produced appropriate conditions. The coincidence of matter-antimatter asymmetry represents another puzzle. The universe contains matter, but essentially no antimatter, approximately 1,000,000,001 matter particles for every 1,000,000,000 antimatter particles in the early universe, with the antimatter annihilating and leaving the small excess as all matter today. This asymmetry must have been generated somehow, as the Big Bang should have produced matter and antimatter equally. Explaining the specific asymmetry value that allows substantial matter to survive while not being so large as to create different structure requires understanding baryogenesis mechanisms. Anthropic principle interpretations of fine-tuning suggest that we observe these values because only universes with such values allow observers to exist. The weak anthropic principle is uncontroversial. We necessarily observe a universe compatible with our existence. The strong anthropic principle suggests the universe must have properties allowing observers, which is more controversial as it might imply purpose or design. Anthropic reasoning becomes more compelling in multiverse contexts where many universes with different properties exist, and we necessarily inhabit one compatible with observers. Multiverse proposals suggest our universe is one among many with different physical constants. In eternal inflation scenarios, different regions of space-time undergo inflation and reheating, potentially with different vacuum states corresponding to different physics. In string theory landscape scenarios, perhaps 10 to the 500 different vacuum states exist, each corresponding to different low-energy physics and constants. If the multiverse is real, observing fine-tuning in our universe is unsurprising. We necessarily inhabit a rare universe compatible with life, regardless of how rare such universes are. Criticisms of anthropic and multiverse explanations emphasize lack of testability and explanatory power. If anything we observe can be explained by anthropic selection, the explanations seem unfalsifiable and therefore unscientific. Multiverse proposals might be untestable if other universes are forever beyond observation. These approaches might represent giving up on finding deeper explanations for constants and laws. However, defenders argue that some form of anthropic reasoning is inevitable if multiverses exist, and testability questions are overstated. Multiverse theories can make predictions about probability distributions of observable quantities. Alternative explanations for apparent fine-tuning include that constants are not actually fine-tuned. We might overestimate how sensitive life is to parameters, or forms of complexity we can't imagine might arise with different values. Constants might be determined by deeper theories, eliminating free parameters. A theory of everything might calculate all constants from first principles with no adjustable parameters. The appearance of design might reflect human pattern seeking applied to a sample size of one universe. Evaluating these alternatives requires both better understanding of how constants relate to complexity and progress in fundamental physics. The role of symmetry in determining physical constants has been explored extensively. If the universe possesses certain symmetries, they constrain possible values of constants. Supersymmetry, if it exists, relates bosons and fermions and could explain certain mass relationships. Grand unified theories propose that forces unify at high energies, potentially determining force-strength ratios. String theory's extra dimensions and their compactification determine low-energy physics and constants. These theoretical frameworks attempt to reduce free parameters by invoking symmetries and dynamics, though complete success remains elusive. Naturalness arguments in particle physics suggest that dimensionless ratios should be order unity unless symmetries or dynamics enforce otherwise. The hierarchy problem violates naturalness. The ratio of Higgs mass to Planck mass is approximately 10 to the negative 17, requiring explanation. Some physicists argue that apparent fine-tuning of constants suggests we're missing symmetries or principles that would make the values natural. Others argue that anthropic selection makes unlikely values acceptable if necessary for observers, potentially undermining naturalness as a guiding principle. The experimental search for time variation in fundamental constants tests whether they're truly constant. If constants vary over cosmic time or space, this would indicate they're not fundamental, but rather environmental parameters determined by fields that vary. Measurements of spectral lines from distant quasars constrain variations in the fine structure constant, the combination of fundamental constants determining electromagnetic interaction strength to less than approximately 1 part in a million over billions of years. Proposed variations remain consistent with zero, though improved measurements continue. The origin of cosmic structure from tiny quantum fluctuations inflated to cosmic scales remains incompletely understood. The large-scale structure of the universe, galaxies, clusters, superclusters, filaments, and voids, originated from microscopic quantum fluctuations in the very early universe. Cosmic inflation stretches these quantum-scale perturbations to astronomical scales, providing initial seeds for gravitational collapse. While this general picture is well established, details of inflation and how quantum fluctuations become classical density perturbations involve profound conceptual puzzles about quantum mechanics and cosmology. Inflation proposes that the universe underwent exponential expansion in its first fraction of a second, driven by a scalar field called the inflaton. During inflation, the universe's size increased by a factor of approximately 10 to the 26 or more, in approximately 10 to the negative 35 seconds. A region smaller than an atom expanded to meters or kilometers. This explosive expansion solves several cosmological problems, including the horizon problem, why causally disconnected regions have similar properties, and the flatness problem mentioned earlier. The inflaton field driving inflation has potential energy that dominates during inflation, acting like dark energy causing exponential expansion. As the field slowly rolls down its potential energy converts to kinetic energy, and inflation eventually ends when the field reaches its minimum and oscillates, with oscillation energy converting to radiation and particles in reheating. Different inflation models propose different potential shapes and dynamics, making varied predictions. Quantum fluctuations in the inflaton field during inflation provide the seeds of structure. Quantum mechanics requires that field values fluctuate. The Heisenberg uncertainty principle prevents the field from having precisely defined values everywhere. During inflation, these microscopic quantum fluctuations are stretched to macroscopic scales by the exponential expansion. Regions where the inflaton field had slightly higher or lower values than average expand to enormous sizes, creating density perturbations that later grow gravitationally into galaxies and structure. The transition from quantum to classical, how quantum fluctuations become classical density perturbations, involves deep conceptual questions. Quantum fluctuations exist in superpositions until measured, but the cosmic perturbations we observe behave classically. They have definite amplitudes, not quantum superpositions. How and when does this quantum to classical transition occur? Does it require decoherence through interaction with environment, and what constitutes the environment for the entire universe? Does it require observation or measurement, and who observes the early universe? Decoherence offers a partial explanation. Interactions with environment cause quantum systems to lose coherence and behave classically. For inflaton fluctuations, interactions with other fields or with short wavelength modes of the inflaton itself might provide decoherence. Calculations suggest decoherence can occur on timescales much shorter than inflationary expansion timescales, allowing classical behavior to emerge. However, questions remain about whether decoherence fully solves the measurement problem or merely sweeps it under the rug. The power spectrum of fluctuations, how fluctuation amplitude depends on scale, is predicted by inflation and measured from the CMB and large-scale structure. Inflation predicts an approximately scale-invariant spectrum where fluctuation amplitude is roughly independent of scale, corresponding to a spectral index NS approximately equal to 1. Measurements yield NS approximately 0.965, close to but slightly below 1, indicating slightly more power on large scales than small, a subtle deviation from perfect scale invariance. The spectral index deviation from unity provides information about inflation dynamics. The value relates to how fast the inflaton rolls. Slower rolling produces closer to scale-invariant spectra. The measured value is consistent with simple single-field slow-roll inflation models, where one field slowly rolls down a smooth potential. More complex models with multiple fields, sharp features in the potential, or non-standard dynamics could produce different spectral indices and other observational signatures. Tensor modes, gravitational waves produced during inflation, provide potential smoking gun evidence for inflation. Inflation produces a background of primordial gravitational waves with amplitudes depending on the energy scale of inflation. These tensor modes would imprint characteristic polarization patterns in the CMB called B-modes. Detecting B-modes would confirm inflation and constrain the energy scale, but observations so far have only set upper limits. The BICEP-2 experiment in 2014 reported B-mode detection later attributed to dust, highlighting detection challenges. Non-Gaussianities, deviations from Gaussian statistics in the distribution of fluctuations, provide additional tests of inflation. Simple single-field slow-roll inflation predicts nearly Gaussian fluctuations. Multi-field models, non-standard kinetic terms, or interactions during inflation can produce non-Gaussianities. Measurements from Planck constrain non-Gaussianity to be small, ruling out some inflation models, but remaining consistent with many others. Future observations might detect small non-Gaussianities that would discriminate among models. The eternal inflation problem arises in some inflation models. If inflation is driven by quantum fluctuations as well as classical rolling, then in some regions quantum fluctuations might push the field up its potential, causing continued inflation, while in other regions the field rolls down and inflation ends. The regions where inflation continues expand faster than regions where it ends, so inflation never globally ends, it's eternal, even though it ends locally in various regions, including ours. This leads to a multiverse of bubble universes with potentially different physics. Alternatives to inflation have been proposed to explain the universe's observed properties. The cyclic or ekpyrotic scenario proposes the universe undergoes cycles of expansion and contraction, with structure arising during contraction phases. Varying speed of light theories propose the speed of light was much higher in the early universe, allowing horizon-scale communication and homogenization. Bouncing cosmologies propose the universe contracted from a previous phase, bounced, and then expanded. Each alternative faces theoretical challenges and makes different predictions, with inflation remaining the leading paradigm. The initial conditions for inflation, what set up the inflaton field in the appropriate state, remain mysterious. Inflation requires the inflaton field to start in a relatively homogeneous state, over regions larger than a Hubble volume. How did such homogeneity arise without prior inflation, and doesn't this just push the problem back? Some invoke quantum cosmology or tunneling from nothing, but these approaches involve speculative quantum gravity. The initial conditions problem represents a frontier where inflation connects to deeper questions about the universe's origin. The measure problem in eternal inflation asks how to compute probabilities in an infinite multiverse. If inflation is eternal, infinitely many regions undergo reheating and form bubble universes. Any type of universe that can occur will occur infinitely many times. How do we compute the probability of observing particular properties when both numerator and denominator are infinite? Different measures, prescriptions for regulating infinities, give different predictions. The measure problem remains unresolved and represents a challenge for making eternal inflation predictive. Quantum cosmology attempts to describe the universe's origin using quantum mechanics. The Wheeler-DeWitt equation, a version of the Schrödinger equation for the entire universe, provides a framework, though interpreting it is challenging. The Hartle-Hawking no-boundary proposal suggests the universe has no initial boundary. Going back in time, spacetime transitions from Lorentzian to Euclidean signature, avoiding a singularity. The Violating tunneling proposal suggests the universe tunneled from nothing. These approaches involve speculative quantum gravity and remain controversial. The observational constraints on inflation continue improving. The Planck satellite measured CMB temperature and polarization with unprecedented precision, constraining inflation parameters including spectral index, tensor-to-scalar ratio, and non-Gaussianity. Future CMB experiments targeting B-mode polarization may detect primordial gravitational waves or further constrain their amplitude. Large-scale structure surveys measure matter distribution, constraining inflation predictions. Together, these observations narrow the space of viable inflation models while testing the paradigm's foundations. The role of higher-order corrections in inflation calculations has received attention. Standard inflation calculations use leading-order approximations, but higher-order quantum corrections can potentially modify predictions. Loop corrections in quantum field theory during inflation might affect power spectrum predictions or introduce new observational signatures. Understanding these corrections requires non-equilibrium quantum field theory in curved spacetime, a technically challenging calculation regime where results remain debated. The matter-antimatter asymmetry of the universe lacks a complete explanation despite progress in understanding baryon number violation. The observable universe consists overwhelmingly of matter rather than antimatter, yet the Big Bang should have produced equal amounts of both. Understanding how this asymmetry arose, baryogenesis, represents a major unsolved problem connecting particle physics and cosmology. The solution requires physics beyond the standard model and has implications for the nature of matter and the possibility of antimatter galaxies. Antimatter consists of particles with the same masses as matter particles, but opposite charges and other quantum numbers. The positron is the antiparticle of the electron, same mass, opposite charge. Antiprotons and antineutrons are antiparticles of protons and neutrons. When matter and antimatter meet, they annihilate, converting mass entirely to energy. If the early universe had equal matter and antimatter, they should have annihilated completely, leaving only radiation. Yet we exist, as does all matter around us. Observations confirm the matter domination extends to cosmological scales. If significant antimatter existed in the universe, matter-antimatter annihilation at boundaries would produce characteristic gamma rays. Observations from satellites including PAMELA and AMS detect very few antiparticles in cosmic rays, consistent with them being secondary products of cosmic ray interactions rather than primordial antimatter. The gamma-ray background shows no evidence of annihilation signatures at scales suggesting antimatter galaxies or clusters. Matter dominates to at least cluster scales, possibly throughout the observable universe. The magnitude of the asymmetry is approximately 1 part in a billion. For every billion antimatter particles in the early universe, there were 1,000,000,001 matter particles. After annihilation, the small excess of matter particles survived, becoming all the matter we observe. This ratio is determined by comparing the current baryon density, approximately 1 proton per cubic meter, to the photon density, approximately 400 photons per cubic meter, a remnant from annihilation. Sakharov conditions specify requirements for generating matter-antimatter asymmetry. In 1967, Andrei Sakharov identified 3 necessary conditions. Baryon number violation. Processes must exist that don't conserve baryon number, allowing net baryon creation. C and CP violation. Processes must distinguish between matter and antimatter. And departure from thermal equilibrium. Reactions must occur out of equilibrium to prevent the asymmetry from being washed out. All 3 conditions are necessary, and understanding how they're satisfied reveals the asymmetry's origin. Baryon number violation is not present in the standard model at the classical level. Baryon number is conserved in all standard model interactions. However, quantum effects including anomalies and sphalerons can violate baryon number. Electroweak sphalerons, topological transitions in the early hot universe, violate baryon and lepton number while conserving BL, the difference between baryon and lepton number. These processes were efficient at temperatures above the electroweak scale, potentially erasing any pre-existing asymmetry, but also offering mechanisms for generating asymmetry. CP violation, violation of combined charge conjugation and parity symmetry, is observed in particle physics, particularly in quark sector weak interactions. The CKM matrix describing quark mixing contains a complex phase allowing CP violation. However, standard model CP violation appears insufficient to generate the observed asymmetry. Calculations suggest it produces asymmetries orders of magnitude too small. Additional CP violation beyond the standard model is likely required. Grand unified theories, or GUTS, propose that electromagnetic, weak, and strong forces were unified at very high energies, approximately 10 to the 15 GeV or higher. GUTS generically predict baryon number violation through heavy particle decays. If heavy bosons predicted by GUTS decay asymmetrically to quarks versus antiquarks due to CP violation, and if this occurs out of equilibrium during the universe's cooling, the Sakharov conditions are satisfied. However, gut-scale baryogenesis requires very high temperatures after inflation, reheating temperatures above approximately 10 to the 9 GeV, which might conflict with gravitino constraints in supersymmetric theories. Leptogenesis proposes generating a lepton asymmetry that's partially converted to a baryon asymmetry by sphalerons. Heavy right-handed neutrinos, hypothetical particles that could explain neutrino masses through the seesaw mechanism, might decay asymmetrically to leptons versus antileptons due to CP violation in the neutrino sector. Sphaleron processes convert some of this lepton asymmetry to baryon asymmetry before the electroweak phase transition. Leptogenesis is attractive because it connects to neutrino physics and can work at lower temperatures than gut baryogenesis. Electroweak baryogenesis proposes that the asymmetry is generated during the electroweak phase transition at temperatures approximately 100 to 200 GV. For this mechanism to work, the phase transition must be strongly first-order, proceeding through bubble nucleation rather than smoothly, and sufficient CP violation must exist. In the standard model, the phase transition is too weak and CP violation is too small. Extensions including supersymmetry or extended Higgs sectors can strengthen the phase transition and add CP violation, making electroweak baryogenesis viable. Spontaneous baryogenesis proposes that baryon number violation is driven by a time-varying scalar field that couples to baryon current. As this field evolves during the early universe, it creates an effective chemical potential for baryon number, causing baryons to be produced preferentially over antibaryons. This mechanism can work even in thermal equilibrium, partially relaxing Sakharov conditions. Various implementations in inflation models or other scenarios have been explored. Asymmetric dark matter models propose that dark matter has a matter-antimatter asymmetry with magnitude related to the baryon asymmetry. If dark matter and ordinary matter asymmetries are generated by a common mechanism, their densities might be related, potentially explaining why dark matter and baryonic matter densities are within an order of magnitude despite being very different types of particles. These models can provide alternative baryogenesis mechanisms and predict dark matter properties, including mass scales around GV. Experimental searches for baryon number violation include proton decay searches. Many guts predict protons should decay, though with extremely long lifetimes, greater than approximately 10 to the 34 years. Experiments including superkamiokan search for proton decay by monitoring large volumes of ultrapure water for decay signatures. No decays have been observed, setting limits on proton lifetime exceeding 10 to the 34 years for some decay modes, constraining or ruling out some gut models. Neutron-antineutron oscillation represents another baryon number violating process. If neutrons can oscillate into antineutrons, this violates baryon number by 2 units. Such oscillations are predicted by some beyond standard model theories. Experiments search for these oscillations by looking for annihilation signatures when antineutrons interact with nuclei. Current limits set oscillation times greater than approximately 10 to the 8 seconds, but future experiments could improve sensitivity. The cosmic matter-antimatter asymmetry remains observationally constrained. If antimatter existed in significant quantities anywhere in the observable universe, we should detect signatures. Observations of galaxy clusters through X-ray and gamma-ray telescopes show no evidence of annihilation at cluster boundaries. The uniformity of the CMB argues against large antimatter domains. Boundaries between matter and antimatter regions would create distortions. These observations constrain, but don't definitively exclude distant antimatter galaxies or domains. Primordial antimatter searches in cosmic rays look for antiparticles including antiprotons, antihelium, and antideuterium. While antiprotons are detected, produced as secondary particles when cosmic rays hit the interstellar medium, antihelium and heavier antinuclei are extremely rare, consistent with 0 detections by AMS. A single confirmed antihelium detection would imply antimatter stars or galaxies somewhere, as no known mechanism produces antihelium secondarily in significant quantities. Continued searches might reveal surprises. The connection between baryogenesis and dark matter genesis through unified mechanisms has motivated theoretical work. If asymmetry relates baryon number and dark matter number, their generation might be linked. Scenarios where dark matter is a baryon, for example, exotic stable hadrons, or where dark matter genesis and baryogenesis share common dynamics, have been explored. These unified frameworks could potentially explain the cosmological coincidence that dark matter and baryonic matter densities are similar orders of magnitude. The role of phase transitions in baryogenesis extends beyond electroweak baryogenesis. First-order phase transitions can provide the departure from equilibrium needed for Sakharov conditions. Bubble walls during phase transitions can create the requisite non-equilibrium conditions. CP violating processes at bubble walls can generate asymmetries. This mechanism might operate at various energy scales depending on what phase transitions occurred in the early universe. Understanding early universe phase transitions is thus crucial for understanding baryogenesis possibilities. The arrow of time appears to emerge from the universe's low entropy initial state, but lacks fundamental explanation. Time appears asymmetric. Past differs from future in obvious ways, including memory existing for past but not future, aging proceeding in one direction, cups breaking but not spontaneously reassembling. This arrow of time relates to entropy and the second law of thermodynamics, which states that entropy, disorder, increases. Yet the fundamental laws of physics are time-symmetric, creating a puzzle about why time has a direction. The second law of thermodynamics states that in isolated systems, entropy tends to increase or stay constant, never spontaneously decreasing. This explains many irreversible processes. Heat flows from hot to cold, not reverse. Gases expand to fill containers, not spontaneously compress. Organized systems become disorganized unless work is input. Entropy increase provides an arrow of time distinguishing past from future. The past is the direction of lower entropy. The statistical interpretation of entropy, developed by Boltzmann, explains the second law. Entropy measures the number of microscopic states corresponding to a macroscopic state. Higher entropy means more possible microscopic configurations. Systems evolve from ordered, low-entropy states with few microscopic possibilities to disordered, high-entropy states with many possibilities, simply because there are more ways to be disordered than ordered. This makes entropy increase probable, not certain. Fluctuations to lower entropy are possible but rare. The puzzle is why the universe has low entropy in the past. If the second law explains the arrow of time by saying entropy increases from past to future, what explains why entropy was low in the past? Going back in time, entropy was lower and lower, until we reached the Big Bang where entropy was apparently extremely low. The universe began in a highly ordered state. Why? The fundamental laws don't require this. They're time-symmetric and would equally allow a high-entropy beginning. The low-entropy initial condition appears fine-tuned. Roger Penrose calculated that the probability of the universe randomly starting in a state as ordered as ours is approximately 1 in 10 to the 10 to the 123, an extraordinarily small number. This suggests the low-entropy start is not random, but requires explanation. Yet we have no widely accepted explanation for why the universe began with such low entropy. Gravitational entropy complicates the picture. For most systems, maximum entropy corresponds to uniform distributions, gas uniformly filling a container. But gravity is different. Gravitational systems have negative heat capacity, and maximum entropy might correspond to black holes, which concentrate mass. The early universe was smooth and homogeneous, normally high entropy, but gravitationally this is low entropy because gravity favors clumping. As structure forms, gravitational entropy increases despite the universe appearing more ordered. Black holes contribute enormously to cosmic entropy. The Bekenstein-Hawking entropy of a black hole is proportional to its horizon area. A supermassive black hole can have entropy 10 to the 90 or higher, dwarfing the entropy of stars, galaxies, or radiation. As the universe evolves and more mass falls into black holes, entropy increases dramatically. In the far future, black holes might dominate cosmic entropy, with maximum entropy achieved when all matter has collapsed into black holes. The cosmological arrow of time connects to expansion. Some have proposed that time's direction relates to expansion. The arrow points in the direction of increasing universe size. However, this seems coincidental rather than causal. Time-symmetric laws govern expansion, and in contracting universe phases, entropy would still increase in the same direction. The expansion provides a cosmological clock, but doesn't obviously explain entropy increase. The psychological arrow of time, our experience of time flowing from past to future, might emerge from the thermodynamic arrow. Our memories form through entropy-increasing processes. Writing information in brain states corresponds to increasing entropy. We remember the past, but not the future, because we can record past events in brain states, but not future ones. If time ran backward thermodynamically, our subjective experience might also reverse, though this is highly speculative. The quantum measurement arrow of time relates to wave function collapse or decoherence. Quantum systems exist in superpositions that collapse or decohere upon measurement, creating definite outcomes. This process appears time-asymmetric. Superpositions evolve to definite states, not the reverse. However, whether this represents a fundamental time asymmetry or emerges from thermodynamic considerations about measurement apparatus is debated. Decoherence is fundamentally entropy increasing, connecting quantum measurement to thermodynamics. The weak nuclear force exhibits CP violation, which combined with CPT symmetry under combined charge conjugation, parity, and time reversal, implies T violation, or time reversal asymmetry. However, this fundamental time asymmetry is very weak and appears unrelated to the macroscopic arrow of time. The amount of CP violation in the standard model is far too small to explain thermodynamic irreversibility. It remains unclear whether fundamental time asymmetry connects to macroscopic arrows. Causal asymmetry, causes precede effects, seems deeply connected to the thermodynamic arrow. We say a cause is B if manipulating a changes B, and this manipulation concept assumes we can intervene from a low entropy past, creating correlations pointing to the future but not past. If entropy increased in the opposite direction, our notion of causation might reverse. Causation might not be a fundamental feature of physics, but an emergent concept in systems with entropy gradients. The possibility of time-reversed universes has been considered. If a universe contracts after expanding, would entropy decrease during contraction, with arrows of time reversing? In traditional thermodynamics, entropy should continue increasing even during contraction. Gas remains in high entropy states regardless of expansion or contraction. However, some proposals suggest entropy might decrease in contracting phases, creating time symmetry about maximum expansion, though this requires special dynamics. The past hypothesis proposes that the universe's low-entropy initial state should be taken as a fundamental postulate or law of nature. Rather than seeking a deeper explanation, we simply accept that the universe began in a low-entropy state, and all temporal asymmetries follow. Critics argue this is unsatisfying. It merely labels the puzzle rather than solving it. Proponents counter that some boundary conditions must be postulated, and the past hypothesis is a relatively simple one. Multiverse and anthropic explanations propose that in an ensemble of universes with different initial conditions, only those with low entropy beginnings allow observers like us to exist. If entropy were not low initially, stars, planets, and complex chemistry couldn't develop, preventing life and observers. We necessarily find ourselves in a universe with a low entropy start. This explanation is controversial. It might explain why our universe has low initial entropy, but not why the multiverse allows such variation, or why universes exist at all. The emergence of time's arrow from the universe's quantum state is explored in quantum cosmology. The Wheeler-DeWitt equation is timeless. It contains no time parameter. Time might emerge from the quantum state through decoherence and the correlation of system clocks with system configurations. The arrow might emerge from the particular quantum state of the universe, though making this precise is challenging. These approaches are highly speculative, but represent attempts to derive the arrow of time from more fundamental considerations. The relationship between cosmic inflation and entropy requires careful consideration. Inflation dramatically increases the universe's volume, and if each volume element has similar entropy, total entropy increases enormously. However, the smooth post-inflation universe has lower entropy per volume than a maximally entropic state would have. Gravity hasn't yet clumped matter into black holes. Inflation creates a low gravitational entropy state that then increases as structure forms. Understanding how inflation sets initial conditions for entropy increase remains an active area. The role of quantum fluctuations in establishing time asymmetry has been explored. If quantum fluctuations during inflation are the seeds of structure, and if the quantum to classical transition involves decoherence, which is entropy increasing, then the arrow of time might emerge from quantum cosmology. The measurement-like processes during decoherence would establish records, classical perturbations, pointing toward the future. This connects the psychological arrow of time recording memories to the cosmological arrow, establishing classical density perturbations. The Fermi paradox asks why we see no evidence of extraterrestrial intelligence despite the universe's vast scale and age. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, many with planets. Over billions of years of cosmic history, one might expect numerous civilizations to have arisen. Yet we detect no signs of advanced technological civilizations, no radio signals, megastructures, or other technosignatures. This absence constitutes the Fermi paradox, named for Enrico Fermi, who reportedly asked, "Where is everybody?" The Drake equation provides a framework for estimating the number of communicative civilizations in the galaxy. It multiplies factors including the star formation rate, the fraction of stars with planets, the number of habitable planets per star system, the fraction where life arises, the fraction where intelligence evolves, the fraction that develop technology, and the lifetime of technological civilizations. While uncertain, some parameter choices yield large numbers of civilizations, making the silence surprising. The number of potentially habitable planets appears enormous. Kepler mission observations suggest approximately 20 to 50% of Sun-like stars have rocky planets in habitable zones, regions where liquid water could exist on surfaces. The Milky Way contains approximately 200 to 400 billion stars, implying tens of billions of potentially habitable planets in our galaxy alone. This suggests numerous opportunities for life, even if it's rare per planet. The timescale argument strengthens the paradox. The universe is approximately 13.8 billion years old, while Earth is 4.5 billion years old, and life appeared relatively quickly in geological terms. Many stars and planets are much older than Earth. Even if interstellar travel is slow, say 1% light speed, a single expanding civilization could colonize the galaxy in tens of millions of years, a cosmologically brief period. Given billions of years available, the galaxy should have been colonized long ago if technological civilizations are common. SETI, the search for extraterrestrial intelligence, has conducted systematic searches since 1960 with no confirmed detections. Radio SETI searches for narrowband signals or other patterns distinguishable from natural emissions. Optical SETI searches for laser pulses. Recent efforts including breakthrough LISTEN conduct sensitive searches across wide frequency ranges and many target stars. The null results constrain, but don't exclude possibilities. The search space is vast, and signals might use unfamiliar technologies, frequencies, or modulation schemes. Possible explanations for the Fermi paradox include rare Earth scenarios where life or intelligence is far rarer than assumed great filter scenarios where civilizations face existential challenges preventing longevity, zoo hypotheses where advanced civilizations intentionally avoid contact, and various practical limitations on interstellar travel or communication. Each explanation has strengths and weaknesses, and multiple factors might contribute. The rare Earth hypothesis proposes that complex life requires numerous low-probability conditions. Requirements might include Earth-mass planets, large moons stabilizing axial tilts, Jupiter-mass planets deflecting comets, moderate eccentricity orbits, appropriate stellar metallicity, location avoiding galactic dangers like supernovae and gamma-ray bursts, and plate tectonics recycling carbon. If many such factors are needed, habitable planets might be far rarer than naive estimates suggest, potentially making intelligent life very rare. The Great Filter represents one or more extremely difficult evolutionary steps between non-life and expanding civilizations. If the filter is in our past, for example, abiogenesis or the evolution of eukaryotic cells, we've passed it, suggesting intelligence might be rare but not necessarily doomed. If the filter is in our future, perhaps self-destruction via nuclear war, climate change, artificial intelligence, or other technology, our prospects are grim, and the silence reflects civilizations failing to survive. Determining filter location has profound implications. Self-destruction scenarios propose that technological civilizations inevitably destroy themselves before becoming long-lived or expansive. Nuclear weapons, engineered pandemics, runaway climate change, hostile artificial intelligence, or unknown future technologies might pose existential risks that civilizations rarely navigate successfully. The fact that we've developed dangerous technologies within a century of radio and the rapidity of technological change might suggest a narrow window between capability and catastrophe. The zoo hypothesis proposes that advanced civilizations exist but deliberately avoid contact, perhaps to allow natural development or for ethical reasons analogous to protecting uncontacted tribes. This requires coordination among all civilizations and sustained commitment over geological timescales. Both seem implausible if civilizations are numerous and diverse. Moreover, it anthropomorphizes alien motivations, which might be fundamentally different from ours. Physical or practical limitations might prevent interstellar expansion. Interstellar travel is enormously difficult, distances are vast, energy requirements are huge, and relativistic effects complicate journeys. Self-sustaining interstellar colonies might be harder than assumed. Civilizations might be planet-bound for fundamental reasons we don't appreciate. Communication might face challenges including signal degradation, time delays making dialogue impractical, or competition with natural astrophysical sources. Detection challenges might explain the absence of observed signals. Civilizations might use communication technologies we haven't developed or don't recognize. For example, neutrino communication, modulated gravitational waves, or quantum entanglement if that allows communication, which current physics suggests it doesn't. They might use narrowbeam rather than broadcast communication for efficiency, reducing detection probability. Our searches have sampled only a tiny fraction of possible star systems, frequencies, times, and signal types. The intelligence is rare. Explanation proposes that while life might be common, intelligence and technology are rare. Earth's history shows life emerged quickly, but intelligence took billions of years, with numerous contingencies required. Most species are unintelligent, and humans might be a rare accident. Tool use, language, cumulative culture, and science might require unlikely evolutionary paths. If intelligence is a rare outcome even given billions of years of evolution, civilizations might be very sparse. The short lifetime explanation proposes that technological civilizations exist, but don't persist long enough to overlap in time or space with us. If typical civilizations last thousands or even millions of years before extinction, the probability of detecting one depends on their spatial density and our limited observational capabilities. Given the galaxy's size and age, numerous civilizations could have risen and fallen without ever being detected by us or each other. Transcension hypotheses propose that advanced civilizations might transcend physical reality in ways making them undetectable, for example, uploading consciousness to Competronium, moving to extra dimensions, or creating simulated universes and inhabiting those. If physical reality is a temporary stage before such transcension, the observable universe might lack advanced civilizations because they've moved beyond detection. The simulation hypothesis proposes our universe is a simulation created by an advanced civilization. If creating simulations is possible, and civilizations commonly do it, simulated universes likely vastly outnumber base reality, making it probable we're in a simulation. This might explain Fermi paradox if simulators limit detectable civilizations in simulations for computational efficiency or narrative purposes. However, the hypothesis is unfalsifiable with current knowledge and raises philosophical questions. Recent developments, including detection of thousands of exoplanets, increased understanding of habitability requirements, and expanded SETI capabilities, have refined the paradox without resolving it. UAP, unidentified aerial phenomena, reports have generated renewed discussion, though no confirmed evidence of extraterrestrial technology exists. The paradox remains among the most profound questions in science, touching on biology, physics, sociology, and philosophy. The implications of Fermi paradox resolutions vary dramatically. If we're alone or nearly so, humanity has enormous cosmic significance and responsibility. We might represent the universe's only opportunity for self-understanding. If we're common but short-lived, we face existential threats requiring urgent attention. If we're in a crowded galaxy but undetected, our search strategies need revision. Each resolution carries different implications for action and meaning. The cultural impact of detecting extraterrestrial intelligence would be profound, regardless of the signal's content. Confirmation that we're not alone would reshape philosophy, religion, science, and society. Even a simple beacon confirming others exist would answer fundamental questions about life's prevalence and our cosmic context. Protocols for responding to detection exist, but predicting actual responses is difficult. The absence of detection so far has its own implications, constraining how common technological civilizations are. The relationship between the Fermi paradox and existential risk has motivated some researchers to study catastrophic risks more seriously. If the great filter is ahead of us, identifying and mitigating existential risks becomes humanity's highest priority. Nuclear war, engineered pandemics, unaligned AI, and other risks might represent common failure modes for technological civilizations. Understanding and addressing these risks might determine whether humanity becomes spacefaring or joins the hypothetical graveyard of failed civilizations. If you're still awake somewhere in this exploration of universe mysteries, of dark matter and dark energy, of black hole paradoxes and fine-tuned constants, of cosmic inflation and antimatter asymmetry, of time's arrow and Fermi's question, there's more to discover about the profound unknowns of existence. But if sleep has found you, if consciousness has faded into dreams, then rest knowing that the universe continues its mysterious operations, expanding, evolving, and perhaps harboring secrets we've not yet imagined. While you sleep tonight, the universe is expanding around you. Every galaxy outside our local group is receding, carried away by the expansion of space itself. Dark energy, whatever it is, drives this acceleration, pushing galaxies apart at ever-increasing rates. Eventually, all galaxies beyond our local group will recede beyond our cosmic horizon, becoming forever unobservable as the space between us and them expands faster than light can traverse. The long-term fate of the universe depends on dark energy's nature, determining whether expansion continues forever, accelerates to a big rip, or reverses to a big crunch. Dark matter, 5 times more abundant than ordinary matter, creates the gravitational scaffolding supporting cosmic structure. Invisible to electromagnetic radiation, it reveals itself only through gravity. Dark matter halos surround galaxies, including the Milky Way. You're currently embedded in such a halo, with dark matter particles perhaps passing through your body and the Earth every second. Direct detection experiments deep underground are watching for the rare interactions when dark matter strikes ordinary matter, seeking to identify what dark matter is after decades of null results. Black holes throughout the universe, from stellar mass remnants to supermassive monsters in galaxy centers, continue accreting matter while slowly evaporating through Hawking radiation. Information about everything that fell into them might be preserved in subtle correlations in Hawking radiation, or encoded in horizon degrees of freedom, or lost in violation of quantum mechanics, or something else we don't understand. The resolution awaits progress in quantum gravity, a theory unifying quantum mechanics and general relativity that remains elusive. The physical constants governing physics in our observable universe have the values they have for reasons unknown. Why is gravity so weak? Why is the cosmological constant so small? Why are nuclear forces precisely strong enough for stable atoms and long-lived stars? These values might be fixed by a deeper theory or selected anthropically from a multiverse of possibilities or random initial conditions we're stuck with. Each possibility has implications for physics' future and the meaning of scientific explanation. Quantum fluctuations during cosmic inflation, stretched to astronomical scales, seeded the structure we observe. The CMB temperature fluctuations of 1 part in 100,000 grew through gravitational amplification into galaxies and clusters. This inflation occurred in the first fraction of a second, driven by a field we don't understand, producing an expansion we can't explain in detail. The quantum to classical transition, turning quantum fluctuations into definite density perturbations, involves interpretive questions about quantum mechanics that remain unsettled. The matter-antimatter asymmetry permitting our existence, 1 part in a billion more matter than antimatter, arose through mechanisms not fully understood. Somewhere in the early universe's first seconds, processes violating baryon number, CP symmetry, and occurring out of equilibrium created a slight matter excess. As the universe cooled, matter and antimatter annihilated, leaving only the small matter excess as everything we observe. Understanding how this happened requires physics beyond the standard model. Time's arrow points from past to future, from low entropy to high entropy, from organized to disorganized. Why the universe began in a low entropy state remains mysterious. The Big Bang started with incredible organization, smooth and homogeneous, which seems to contradict entropy's tendency to increase, since uniform states normally have high entropy. This initial low gravitational entropy, necessary for our existence, lacks fundamental explanation and might represent a boundary condition we simply accept or an anthropic selection from a multiverse. In the vastness of space, as far as we can observe, no signs of technological civilizations appear. Radio searches detect no artificial signals. No Dyson spheres block starlight. No signs of galaxy-scale engineering exist. This silence, the Fermi paradox, might mean we're alone or early or looking wrong or facing a great filter ahead or any of numerous other explanations. The answer matters enormously for our place in the cosmos and our future prospects. The universe itself might be part of a multiverse, an ensemble of universes with different properties, different physical constants, different initial conditions, or even different physical laws. If eternal inflation produces bubble universes, or if string theory's landscape realizes different vacua in different regions, or if quantum mechanics' many worlds interpretation creates branching realities, then our universe is one among many. This would explain fine-tuning through anthropic selection, but raises questions about testability and explanation's nature. Consider that everything we observe, all light, matter, and radiation, comprises only approximately 5% of cosmic energy density. Dark matter is approximately 27%. Dark energy is approximately 68%. We don't know what most of the universe is. This is humbling and exciting. Humbling because our ignorance is vast, exciting because fundamental discoveries await. Future observations, experiments, and theories will illuminate these mysteries or reveal new ones. The questions facing cosmology and fundamental physics are profound. What are dark matter and dark energy? How do quantum mechanics and gravity unify? Why does the universe have the properties it has? How did structure arise? Why is there something rather than nothing? These questions connect to philosophy, touching on existence, causation, and explanation. Science can address them through observation, experiment, and theory, though answers might require conceptual revolutions. The history of physics shows that mysteries often yield to new perspectives. Planetary motion was mysterious until Newton's laws. Electromagnetic radiation was mysterious until Maxwell's equations. Atomic spectra were mysterious until quantum mechanics. Cosmic expansion was mysterious until general relativity. Current mysteries might similarly await theoretical advances we can't yet imagine, or they might require accepting brute facts about initial conditions or fundamental constants. Either way, the search continues. The universe is comprehensible. We can observe it, model it, predict it, and understand it to remarkable degrees. This comprehensibility is itself mysterious. Why should mathematical equations describe reality? Why should human brains, evolved for survival on African savannas, be capable of understanding cosmology, quantum mechanics, and relativity? The unreasonable effectiveness of mathematics in describing nature, as Eugene Wigner put it, is a mystery of a different sort. Your existence connects to these cosmic mysteries in profound ways. The atoms in your body formed in stars and supernovae. The carbon in your cells, oxygen in your blood, calcium in your bones, all created through nuclear fusion in stellar cores and dispersed through space by stellar deaths. You are quite literally made of stardust. The processes creating heavy elements depend on the fine-tuned constants and the matter-antimatter asymmetry permitting matter to exist. The low entropy beginning of the universe made your existence possible. Without that improbable start, stars wouldn't form, planets wouldn't coalesce, chemistry wouldn't create complexity, and life couldn't arise. Every thought you have, every memory you form, every action you take is enabled by the universe's arrow of time, pointing from that mysterious low-entropy origin toward an increasingly disordered future billions of years away. The dark matter halo surrounding the Milky Way holds our galaxy together, preventing stars from flying apart. Without dark matter, galaxies couldn't form or persist, eliminating the environments where stars like the Sun exist long enough for planets and life to develop. Your existence depends on this invisible mass, whose nature remains unknown. Dark energy will determine the universe's ultimate fate, potentially rendering most of the observable universe forever inaccessible as distant galaxies recede beyond light's ability to reach us. Future civilizations, if any exist, might observe only their local group, with all evidence of the larger universe lost beyond horizons. We live in a special time when the universe's expansion, history, and structure are still observable. A few trillion years hence, that might not be true. The mysteries surrounding you, dark matter, dark energy, black holes, time's arrow, cosmic origins, are not merely academic curiosities, but fundamental puzzles about reality's nature. They remind us how much remains unknown despite centuries of scientific progress. They inspire wonder and humility while motivating continued exploration. They connect the smallest scales of quantum physics to the largest scales of cosmology, suggesting deep unity in nature's laws. See you next time.
you